Welcome to this video on correlation. We'll begin by introducing the concept of correlation and its importance in understanding relationships. Next, we'll explore the types of correlation to see how variables can relate positively, negatively, or not at all. Then, we'll use the scatter diagram as a simple visual tool to interpret correlation. Afterward, we'll define the correlation coefficient and discuss its unique properties that make it essential for measuring relationships. Finally, we'll demonstrate how to calculate the correlation coefficient step by step. Let's get started. Concept of correlation. In many research scenarios, it's essential to examine two variables together to determine if they share a linear relationship. When two quantities change in such a way that increases or decreases in one are reflected by similar changes in the other, they are considered correlated or correlated. This relationship forms the foundation for bivariate data analysis, also known as correlation analysis. Correlation measures the relationship between two variables and shows whether and how strongly pairs of variables are related. For example, does study time in hours relate to marks scored in an examination? Is there a relationship between rainfall and the production of corn? Types of correlation. According to the direction of change in variables, there are two types of correlation: positive correlation, negative correlation. When the changes in the values of two correlated variables are in the same direction, the correlation between them is said to be positive. Example: the height of the lift increases, decreases according to the height of goods increases, the decreases. Perfect positive correlation. If the values of the variable increase or decrease proportionately, then they are said to have perfect positive correlation. Example: since there is a fixed conversion factor between Celsius and Fahrenheit, every increase in Celsius results in a predictable and proportional increase in Fahrenheit. Negative correlation. Correlation between two variables is said to be negative if the values of the variables deviate in opposite directions. That is, if the values of one variable increase or decrease, then the values of the other variable decrease or increase. Example: price increases, demand decreases. Perfect negative correlation. If one variable increases and another decreases proportionately, or if one variable decreases and another increases proportionately, then they are said to have a perfect negative correlation. Example: as you go higher up, every additional increase in altitude would cause an exact proportional drop in temperature. Methods to find correlation. Scatter diagram, correlation coefficient. Scatter diagram. A scatter diagram is the simplest way of representing bivariate data diagrammatically. One variable is plotted along the x-axis and the other along the y-axis. Each pair of values is plotted as a point on a two-dimensional graph. The resulting diagram of points is called a scatter diagram. If the points form a band showing a rising trend from the lower left-hand corner to the upper right-hand corner, the variables are positively correlated. If the points form a band showing a falling trend from the upper left-hand corner to the lower right-hand corner, the variables are negatively correlated. If the points are scattered randomly across the plane, the variables are uncorrelated. If all points lie on a straight line, rising from the lower left-hand corner to the upper right-hand corner, there is a perfect positive correlation. If all points lie on a straight line, falling from the upper left-hand corner to the lower right-hand corner, there is a perfect negative correlation. Let's draw a scatter diagram. Example 1. A company manufactures ready-made garments. The monthly advertisement cost and the sale of garments for the last 6 months are as follows. scenarios. Analysis. Points on the scatter plot do not align on a single line. Advertisement cost and sales increase in the same direction, but not proportionally. This indicates a positive correlation between X and Y. Example 2. The monthly expenditure and monthly savings for 5 middle-class families are as follows. Each family has a monthly income of $20,000. Analysis. Points on the scatter plot align on a single straight line. Monthly expenditure and monthly savings change in opposite directions in a constant proportion. This indicates a perfect negative correlation between X and Y. Correlation coefficient. A scatter diagram tells us whether variables are correlated or not, but it does not indicate the extent to which they are correlated. The correlation coefficient provides a precise measure of the strength of their correlation. The numerical measure of correlation that shows the strength of correlation between two variables is known as the correlation coefficient, R. Popular correlation coefficients are Pearson Correlation Coefficient, Spearman Rank Correlation Coefficient. Let's focus on Pearson Correlation Coefficient. This correlation coefficient, R, introduced by statistician Carl Pearson, is known as the Pearson Correlation Coefficient or Product Moment Coefficient. The Pearson Correlation Coefficient, R, is a statistical measure that quantifies the linear relationship between two variables. It evaluates the strength and direction of the correlation for metric variables. What are metric variables? Metric variables are types of information we can measure with numbers, like weight of an apple, the distance traveled, time taken to finish the puzzle. They tell us how much or how many of something. How is Pearson correlation coefficient calculated? If X and Y are two random variables, the correlation coefficient between them is denoted by R and defined as follows. Xi, individual values of the X variable, Yi, individual values of the Y variable, bar X, mean of the X values, bar Y, mean of the Y values. Steps to calculate the correlation coefficient are: calculate the mean of X, and Y. Subtract these means from each individual X and Y value. 3. Multiply the resulting values for each pair of X and Y. 4. Sum up the products from each pair. The denominator ensures that the correlation coefficient is scaled between -1 and 1. Before we calculate the correlation coefficient, there are a few important rules or assumptions to check. Assumption of linearity, assumption of normality, assumption of cause and effect relationship. Assumption of linearity. To calculate the Pearson correlation coefficient, two metric variables must be present, and they must have a linear relationship. The Pearson correlation coefficient measures the strength of this linear relationship. If the variables are nonlinear, R cannot describe their relationship. Assumption of normality. Both variables should follow a normal distribution, with no significant skew in either direction. Assumption of cause and effect relationship. A cause-effect relationship means one variable directly influences or affects another. Direct cause-effect relationship. If you get a good night's sleep, you feel more energetic the next day. Sleep is the cause. Feeling energetic is the effect. The sale of raincoats and the sale of rain shoes both increased during the monsoon. We cannot tell which variable influences which. Here, the third variable, monsoon, influences both. There must be a direct or indirect cause-effect relationship between the variables, otherwise the correlation is meaningless. Let's do one example. Find the correlation coefficient between advertisement expenditure and profit for the following data. To find the correlation, let X be the advertisement expenditure and Y be the profit. The Pearson's coefficient of correlation formula is used. List the values of variables X and Y. 2. Find the sum of X and Y. Calculate the arithmetic means of X and Y. Take deviations of each observation of X from its mean X, for example, 30 minus 40 equals minus 10, 44 minus 40 equals 4, and so on. Take deviations of each observation from its mean, for example, 56 minus 60 equals minus 4, 55 60 equals minus 5, and so on. Square the deviations of X. Square the deviations of Y. Calculate the product of deviations. Sum each column. Using the values from the table and substituting them into the formula, R equals 0.27. What does this R equals 0.27 mean? To better understand what this number means, let's explore the properties of Pearson's correlation coefficient and how different values reflect varying relationships. Properties of Pearson's correlation coefficient. Property 1. Whenever we calculate the correlation coefficient, its value always lies between -1 and +1. When R equals 1, the two variables have a perfect positive correlation. When R equals -1, the two variables have a perfect negative correlation. When R equals 0, the two variables have no linear correlation. When R is between 0 and 1 and nearer to 1, then there is a high degree of positive correlation. When R is between 0 and 1 and near to 0, then there is a low degree of positive correlation. When R is between -1 and 0 and nearer to 0, then there is a chatter low degree of negative correlation. When R is between -1 and 0 and nearer to -1, then there is a high degree of negative correlation. In our calculated example, text core xy equals R equals 0.27. Since R is between 0 and 1 and closer to 0, there is a low degree of positive correlation between advertisement expenditure and profit. Property 2. The correlation coefficient between X and Y is the same as the correlation coefficient between Y and X. Suppose we're looking at the correlation between study time and exam scores. If we calculate the correlation coefficient for study time, X, and exam scores, Y, and it comes out as R equals 0.8, then if we switch them to be exam scores, X, and study time, Y, we'd get the same value, R equals 0.8. The correlation coefficient between X and Y is the same as the correlation coefficient between Y and X. Property 3. The correlation coefficient is free from units of measurement. For example, When studying the correlation between height and weight, measuring height in inches and weight in pounds gives a correlation coefficient of R equals 0.7. Switching to height in centimeters and weight in kilograms still results in R equals 0.7. Regardless of whether you use inches, pounds, or centimeters per kilogram, the relationship between height and weight remains the same, so the correlation coefficient is unchanged. Property 4. The correlation coefficient is unaffected by changes in scale and origin. What is change of origin and change of scale? A constant is added or subtracted from the values of a variable. It changes the origin on the graph but does not alter the relative position of the data points. What is a change of scale? When a positive constant is multiplied or divided with the values of a variable, it changes the unit scale on the axis, but the relative positioning of the data points remains the same. Let's check with an example. Scatterplot and calculated coefficient of correlation between reading hours and marks are core x, y equals r equals 0.96. To verify the change of origin, 10 is added to the values of the variable x. Core xy equals r equals 0.96. The correlation coefficient r remains unchanged after the change of origin. To verify a change of scale, values of the variable y are divided by 10. Core xy equals r equals 0.96. The correlation coefficient r remains unchanged after the change of scale. When variables have large values and their means, x and y, are not whole numbers, calculating the correlation coefficient can be tedious. A shortcut method simplifies this by replacing actual means, x feet and y feet, with assumed means, ax and ay, using the property that r is unaffected by changes in scale and origin. Calculation of Pearson Correlation Coefficient shortcut method. The correlation coefficient r is obtained by the formula. Assumed means are used in place of actual means. Xi minus ax equals dx and yi ay, number of pairs of observations. Sum of deviations from assumed means ax, sum of deviations from assumed mean ay, sum of product of deviations from assumed means ax and ay, sum of squares of deviation from assumed mean ax in x series, sum of squares of deviations from assumed mean ai in y series. Let's do one example. Find the correlation coefficient between the heights and weights of the students. Calculate arithmetic means of x and y. With fractional means and large values, the shortcut method is preferred for computing r. Let ax equals assumed mean of x equals 158 and ay equals assumed mean of y equals 56. Deviations from assumed mean in x values. deviations from assumed mean AY in Y values. Squares of deviations from assumed mean AX in X values. Squares of deviations from assumed mean AY in Y values. Product of deviations. Sum of each column. Taking the values from the table and substituting in the formula, we get R equal 0.9821. R is between 0 and 1 and nearer to 1, so there is a high degree of positive correlation between height and weight of the students. Thank you for watching. If you found this video helpful, feel free to like, subscribe, and share it with others who might benefit. Thanks again, and we'll see you in the next video.